All right, should be good to go. Cool. So the agenda for today's class is to essentially go through kinematics, which basically means we're looking at stuff like distance, displacement, speed, velocity, acceleration, all of those essentially applications of, you can think of them as applications of differentiation, but we're more so looking at things in the context of like average rates of change type stuff. So it's not quite differentiation, although it certainly leads up into it. And the topics we'll specifically cover will have some differentiation in there, although the assigned work that actually appears in at least Unit 1 and 2 will be pre-differentiation. This will be more so helpful for also into Year 12, not just the Unit 1 and 2 book. But okay, let's take a look. So first things first, this idea of a position graph. So usually the position graph will be written as some form of x of t, right? Where x is your position and t is time. You're often doing things in that particular notation. One example of that is detailed below. You've got some particular quadratic, and what's essentially happening here is that the y value at any given point measures position with respect to some origin. Now, when I say the word origin, I don't necessarily mean this, because distance from origin would technically be like the straight line from here to here. We don't mean like drawing a straight line connecting to this. We mean that, for instance, here would be considered 7 units away from the origin, whatever the starting point of the scenario is. One thing that's worth pointing out as well is that these are only ever going to be defined for t being greater than or equal to 0. This is because t is representing time, and negative time values would be things going in the past, essentially. So usually not particularly helpful. First thing you'll have to be able to calculate is this idea of the initial position. This will also be true of stuff like initial speed, initial velocity, initial acceleration. Fundamentally, at all times, initial anything is just t equals 0. This is because initial means the starting of the starting condition of the system or the scenario. And that's always going to be at t equals 0 when you start counting time. So we plug in our t equals 0. That's going to give us an initial position of 0, sorry. And so the way you end up interpreting this, if you're asked to interpret it, is you would say that the initial position of the particle is at the origin. That's all we're doing there. Positive initial position. So, okay, there's different kinds of values you can get that come from calculating your initial position. One of the circumstances could be positive, right? For instance, you got an initial position of 4, whatever the unit would be for that. The way you interpret this is you say positive is always right of the origin, right? So this will be 4 units to the right of the origin. Fundamentally, if you look at like the actual path of the particle that will be traveling, it starts at some fixed position 4 units away from the origin, and it will continue moving right. That's because you've got a quadratic, right? So as t gets larger, so too does position. So it'll continue moving right. And you can see that just by plugging in a few different t values. You'll see that your values get larger. And so essentially the way that you would describe this would be to say, particle starts at 4 units right at the origin and continues. Now we can use the word accelerating to the right, because as the time intervals stay the same, the amount of distance that's covered is getting faster and faster. So you could technically say it's accelerating to the right if you wanted to. Though we'll look in more detail how to be specific with our interpretation there. Any questions so far? It's worth pointing out, when you draw these kinds of diagrams for yourself, there is no actual like time information in here. This is simply just your x-axis, and you can just see the direction the particle's moving. You can't necessarily see what time these were. It's like starting at 4, there's no actual information as to how fast or how slow it traveled in that distance. That's why you usually use actual position graphs instead, because you can get a much more in-depth understanding of where it is. Like for instance, this one starts moving left until it reaches 4 units to the left of the origin, then starts coming back, and it takes 4 seconds to do so. Over a period of 4 seconds, it goes 4 units left and then comes back. Then from there, continues to the right at an acceleration. If it's negative, it's left. I kind of already talked about that. Last thing to have a look at, or one of the last things to have a look at here, will be the difference between position and distance. So position is simply a subtraction between where you started and where you ended. That's pretty much it. Distance considers the entire length of the path taken to get there. So for instance, if we were to run a race around a 1 kilometer oval, technically speaking, you start and finish at the same spot, so your displacement is 0. You started and ended at the same spot, 0 minus 0, you got 0. However, distance, you traveled a full 1 kilometer circle, and so for that reason, your distance is 1 kilometer. It really depends on the graph. A decent number of times, your distance and displacement will end up being the same thing. The difference to look for is if your graph has a turning point in it or not. If there is a turning point, your distance is likely going to be different to your displacement, assuming it actually breaches past the turning point, but otherwise it'll be the same. So here we go. We've got a full tilt quadratic. What's the distance and displacement over the first 5 seconds? Really good idea to draw a graph. You want to draw a graph to see if there's any turning points along the way. Doesn't have to be super accurate, like you don't actually care about any of the y value stuff. You simply just care about where the turning point is, if any turning point. We're doing first 5 seconds, that's why it's going to cut off at t equals 5. Remember, t is our x-axis in this case. And so for displacement, very easy. You see it starts at -7, you see it ends at -12. That, or you could calculate each of those, and then you do your subtraction, your displacement ends up being -5 units. So you started higher than you ended. That's why we say negative for that. If you want distance, you essentially have to do it in 2 separate parts. You do the exact same equation, but from start to turning point, and then you add that to turning point to end. And you'll essentially just sort of repeat that for the same number of turning points to show up. Although definitely unit 1 and 2, only one of them are going to show up. I don't think I've ever seen a case where more than one turning point has shown up. But if that was the case, you're essentially dropping it off into sections of turning points. So for instance here, you're doing x of 3 minus x of 0. So it's this one minus this one. And then from here, you're doing from 5 to 3. Another thing worth pointing out, distance can only be positive. We're only allowed to have distance as positive, and that's because the correct terminology for distance is to call it a scalar. So there's these differences between scalars and vectors. Scalars are just the unit of measurement. They don't have any direction associated with them, whereas vectors do, and they use positive and negative signs to determine what the direction is. Displacement is considered a vector, distance is considered a scalar. And so for that reason, any negatives would just be referred to as positives in the context of distance because, because we just want all distance traveled to be positive. Right? It doesn't make sense to walk negative meters.
Chris, does this mean that for displacement we could also be using like bearings and stuff?
I would have to remind myself how to actually use bearings. It's been a very long time.
Okay.
Yeah, I mean, maybe. I know bearings has something to do with like northeast, southwest type stuff. Possibly, yeah. I'd have to really refresh my memory on that one though.
Yeah.
Yeah, I don't think bearings has an appearance in anywhere Unit 1 and 2 or 3 or 4. It's usually one of those things that's like Year 9, Year 10, if not earlier. I don't really remember when it came up. Anyway, sometimes you will get distance being identical to displacement. That's simply going to be if your turning point never really comes into play, or if there just flat out isn't a turning point. Like for instance, if you're doing it from the first 2 seconds, there is no cutoff point. You're doing the exact same thing. The only thing you'd have to worry about is flipping the sign to become positive for distance, because you don't want to have negative in distances. That's distance and displacement. Any things to clarify about that? Whether it be the calculations or the interpretations, anything at all. All right, speed and velocity. So one thing to consider is that your velocity is always going to be the derivative of your displacement graph. Or put in other words, speed is distance over time. It's the slope of the position. One of the things you can do, or that comes up a fair bit, is having to solve things graphically. Right? You're not actually given the equations of any of these lines, although you could find them. It would not be advised because it's not particularly helpful to know the equations of the lines. If all you care about is the velocity, then really all you care about is the slope of each of these lines. You can pretty much only do it if it's straight lines, by the way. As soon as you have any curves, you would have to either be told what type of curve it is, like maybe it's a quadratic, maybe it's an exponential. Otherwise, you wouldn't be able to estimate. You would just have to sort of, sorry, you wouldn't be able to calculate. You would have to just sort of estimate. You wouldn't put any actual like figures to saying it's accelerating or it has this particular velocity. You would just say it's going faster or going at a constant speed or increasing speed, depending on what you're looking at. All of these sections have constant speed, and the reason why is because they have a constant slope. As far as how you're calculating slope, well, you're just doing rise over run, and that becomes your velocity. This one in particular was done in meters per second. Just be mindful of your units. Because it's velocity, you do have positives and negatives. So in this case, you've got a positive slope, a flat slope, and a negative slope. And so when it comes to calculating or plotting your velocity graph, you're essentially just going to, well, draw each of those sections. This, of course, will be a piecewise because you have these sharp connectors, or this it doesn't smoothly join up, and that's why you've got discontinuities at the crossover points. If you remember back when we did limits and continuity, there were a few criteria for a function to be continuous and differentiable. This is a function that is continuous but not differentiable, because at these spots you don't know whether the speed is instantaneously 0, instantaneously 2, or in this case instantaneously -1. We're not actually told enough information to see that. So you're just going to have these sharp gaps. So as far as how to interpret the scenario that we have, one way you could possibly describe the motion of the particle would be as follows. Particle starts at the origin and moves right at a constant velocity of 2 meters per second for a duration of 3 seconds. So talking about position, direction, speed / velocity, and then the duration over which that particular insight is valid. So particle starts at the origin because it starts at 0, 0, moves right because the position values are positive. Positive position means right. You can say what the velocity is because we calculated it, and you can say the time and duration for which it's valid. That's going to apply to basically all sections of this graph. So we would then say the particle remains stationary for a further 7 seconds rather. So instead of saying from t equals 3 to t equals 10, I've just said it was 7 seconds. There's not really strict rules around how you interpret your answer. how you interpret the scenario. Those are just the things I would start bringing up, which is position information as far as what direction it's going, a bit of speed information, and maybe over what duration or time information you can put in there. Probably worth pointing this one out here. There's a couple of ways you could say this last dot point here. I say the particle then moves left towards the origin at a velocity of 1 meter per second. Now, you might look at this and think, hang on a minute, velocity 1 meter per second, shouldn't that be a negative? I don't have to put a negative there because I said it's moving left. If I said it was moving left and then put a negative, I would technically be saying it's moving right. It's like having a double negative in your sentence. The two negatives would cancel, and then suddenly you're saying it's moving right, which is technically incorrect. If you want to put a negative in there, you would not suggest that it's moving left. You would just say the particle then moves at a velocity of -1 meters per second for a duration of 6 seconds until it returns to the origin. Which, might be a bit of a challenge to see here because you still got positive position values, but because the positive position values are getting smaller, it's going left simply because it's not just negative. Sorry, I'll say that again. Negative position values just means it's left of the origin. Positive position values means it's right of the origin. However, when it comes to moving in a particular direction, what matters is where it started and where it ended. Is the nuance on that clear enough on how to interpret these things? This is where the actual calculations are chill. It's more the interpretation where this starts falling apart for most people. So I'm happy to explain any of that in any more detail. All right, we're crushing it. Awesome. If you have the equation for position, then by all means you can solve this stuff using derivative. So we just flat out derive your position equation, get your velocity, and this will be an equation that tells you the velocity of the particle for any given value of t. Note that it's instantaneous velocity because you're doing derivative, right? It won't tell you, we'll look at it a bit later, average speed, right? This is just speed at a particular point. Now, interpreting this graph, we haven't quite talked about acceleration yet. Acceleration is just a derivative of velocity. So one way you could interpret this is to say, okay, it's moving right of the origin at a constantly increasing speed, or specifically you could say it's accelerating to the right at 2 meters per second squared, because the derivative of this would get you to 2. But that's for later. Difference of speed and velocity. Again, this is the difference between scalars and vectors. Speed is a scalar, so it's going to use distance, because distance is a scalar. Velocity is a vector, so it's going to use position for its equation. But fundamentally, these are the same thing. It just depends on which thing you're using to calculate. The actual math is the same, it's just whether you care about distance or position for your particular circumstance. Yeah, velocity is pretty much, you can always get to velocity from derivative. There is no real way to do that with speed, though. What did I say here? Oh yeah, sometimes speed and velocity could come up to be the same thing, depending on the graph, because again, if distance and position have a possibility of being the same, then, well, if you're using those things in your equation, then it follows that speed and velocity could also potentially be the same thing. And once again, it's going to be based on turning points. Apparently I elected not to put a graph in here. It's the same thing, t squared minus 6t minus 7. Yeah, okay. I'll write myself a note to make another copy of this graph and put it in the proper spot. O2, missing graph. My apologies. But yes, this is the graph that we have. Specifically, we're doing it over first 5 seconds, average velocity. So because velocity uses position, first 5 seconds, you're looking at here to here. You find the positions at those spots, which we've seen before. They were -12 and -7 respectively. Over a duration of 5 seconds, that's fundamentally what's happening there. You get your displacement divided by 5. Average velocity is achieved. You don't want to use the velocity equation for this. Like, you don't want to go derivative and then plug in v of 0, v of 5. That's not going to work out too well. Use position values to then calculate that. You only use the velocity equation through derivative if you want to know specifically velocity at t equals 5. Then you would, or at a specific point, rather. For speed, so again, we've got a turning point. So you'd want to, speed needs distance. So you calculate your distance as we have before. And then once you have your full addition of two distances, make sure you make them both positive, then you divide by 5 at the end. Yeah, that's about it. Again, they could be identical. We're just cutting it off before the turning point. Nothing different. Velocity speed, making sure only only speed can be positive, velocity can be both. That's speed and velocity. How are we doing on that? Any questions there? This is probably the hardest point of the kinematic stuff. Acceleration is just another version of this, so it's not harder per se. Anything to clarify? Okay. So essentially what we have is this derivative / integral relationship between position, velocity, and acceleration. You can go up the chain or down the chain with, you can go up with integrals, and you can go down with derivatives. So as long as you know any one of these things, you can always get the other two by using either derivatives or integrals, depending on if you have to go up or down. So a pretty common question that'll come up is to figure out what your position, velocity, and acceleration are, based on just having one of those equations. So in this case, we have velocity. So to get position, we integrate. To get acceleration, we differentiate. Now there's a little bit more to it than that, because when you integrate, you're going to get this plus c that comes along with the equation. In the vast majority of cases, there will be additional information in there to help you solve for c. In this case, the statement is the particle starts at rest at the origin. Only one of those things matters for this particular case, and that's just that the particle starts at the origin. So origin is a position piece of information, which means that when t equals 0, x equals 0. So 0 for x, 0 for t, c is going to come out to be 0. At rest is actually velocity information. It says it has no instantaneous velocity at any given state. So for instance, maybe if you're anti-diffing your acceleration, then that statement of at rest would apply to say velocity is 0 at t equals 0. Yeah, that's about it. Clear enough on those? Okay, next up. So one of the things they'll do after that, once you have those, is to essentially ask you to find the initial state of the scenario. So what is the initial position, velocity, and acceleration? If you remember from earlier, initial just means t equals 0. So you're just plugging in t equals 0 into all these spots and then interpreting from there. Position being 0 means starting at origin. Velocity being 0 means starting at rest. Acceleration being positive, specifically positive 2, means that you are accelerating by 2 meters per second squared to the right. Remember, positive is always right and negative is always left. Or specifically, right of the origin and left of the origin. So when you put that all together, the particle starts at rest at the origin and is about to move right at an initial acceleration of 2 meters per second squared. Average acceleration is kind of nice because it only has velocity. There's no like speed equivalent of acceleration, so you don't have to do any mental gymnastics to figure out which do I use. It's always just going to be velocity. There's your other advantage of using v of t. So if you do have it or have to derive to get it, you use it in calculating average acceleration. And that's the thing that throws people a lot, which is they'll see the words like average acceleration and then use the acceleration equation, or average velocity and use the velocity equation. It's not quite what we're doing. We have to use the previous equation to calculate the average of the next quantity.
Excuse me, Chris.
Yeah.
I'm not sure if I'm like right about this, but like when this is velocity on time, does it mean like the change in velocity over the change in time?
Change in velocity, change in time. Yes,
I
kind
think
of.
that's like how we usually like calculate average acceleration.
Yeah, so it's the same way as in Rise of Iran. The reason why I'm saying not necessarily change in velocity over change in time is because that's usually differentiation type notation, and that's where you start thinking about instantaneous type stuff. So as long as we're on the same page that it is effectively just rise of a run, then yeah.
All right, cool.
Yeah, so it's rise of a run of your velocity. That gets you average acceleration. Now, here's where it gets a little bit weirder because interpretation of acceleration is reliant on velocity. I spent a lot of time trying to figure out how to explain this in the best way. We'll look at a few different scenarios that could come up. So, if velocity is moving in the same direction as acceleration, it would be considered accelerating. So for example, if your velocity and acceleration are both positive, it means the particle is moving right and getting faster. We are accelerating to the right. Now, this is where things get a bit nuanced, so I will just sort of read off the document so I don't mince any words. So this particular scenario here, you've got a thing that's moving in this direction and accelerating in that direction. That is considered accelerating to the right. If they're still both in the same direction but pointing left, you are now accelerating to the left. The other type of scenario is when your velocity is in the opposite direction to acceleration. This is when you have deceleration. So in this example, velocity is negative, but acceleration is positive. That means that your particle is still moving left, but it's getting slower and slower. It's like a car, right? If you drive a car, when you guys can actually drive a car, you don't just instantaneously hit the brakes and then stop and then hit reverse, right? It takes some time to slow down before it can then reverse direction. So when acceleration is pointing in the opposite direction to velocity, we call that decelerating. So essentially what's happening, your car is driving, driver's pressing on the brakes, that is deceleration, right? You're applying an acceleration force in the opposite direction. It'll slow down, slow down, slow down, and eventually make a turn back. That's the difference. So rather than thinking about acceleration positive, acceleration negative, think about its relationship to velocity. That will help you explain things a lot better. Whether you say it's accelerating or decelerating is dependent on that. As for direction, saying left or right, that's pretty much going to come from velocity. This is initially moving left, but give it enough time, it'll eventually start moving right. So, in summary, if they are in the same direction, then the object is accelerating in that direction. If they're in opposite directions, it's decelerating in that direction. This is probably the weirdest part of the entire area of study. If you've got that, then that'd be awesome. Does anyone need me to dive in any deeper into that? Well, there we go. Congratulations. That is all of kinematics done. So that's 16E onwards. So looking at 16E, looking at... Oh, and then chapter review. Cool. So yeah, like not all of that's going to be relevant for this particular chapter. A decent portion of like the derivative stuff especially will be useful for the Unit 3 and 4 version of it. But for now, we just got this to sort of, I guess we'll say ease into it. So what I'll do from here... Yeah. Okay, cool. I'll pull up the classwork document for this, drop that in the chat, and then we'll hop into breakout rooms. So we'll either do this, in which case you're working off the document, or if there's anything in particular you wanted to show me from what you're doing, then we can do that as well. All right, I'll get that sorted. And then bang, bang. Cool, let's rock. Hello. How's it going?
I'm good. How are you?
I'm doing good. All that made enough sense? I know it was a fair bit of content.
Yeah.
That's cool. Nice. Was there anything in particular you wanted me to have a look at?
No question, but could I ask you a question?
Yeah, yeah.
Um, so I did my SAC for calculus and it did not go great, like at all.
Yep. Okay, that's
And
unfortunate to hear.
I was wondering if like you could tell me what you think would be good to do better in my next SAC, like what you think I should be doing to do better. Like if you have any tips or anything.
Yeah, I mean, did you get your paperback or just the result?
Just the result, we didn't get the paper back yet.
What was the result?
40%.
40%. Okay. I mean, I'll be able to give more specific information when I actually see the actual paper. So when you get that, just like send me a photo of it, and I can give you a lot more specific information as to what to work on. Broadly speaking, 40% will typically mean you need to revisit the fundamentals. And a good way to do that would be to hit the chapter reviews of the questions and see how much of those you're getting right, just going into it blind. Like, did you do chapter reviews for study?
No, I just did the practice sack that they gave, but it was nothing like the actual sack.
Yeah, yeah. Well, that's the other thing too. Is it one of those investigation style ones where they I know some schools call them non-routine questions. Was it?
It wasn't like that, but the practice sack that they gave us was like an investigation type.
Oh, okay. So you got investigation and then you got a standard for the actual thing.
Yeah, so it didn't really help.
Yeah, interesting. Well then, yeah, I mean the obvious answer then is do the chapter review stuff, and that's basically a sack. And then there's also my stuff in the classroom tab as well, which is definitely a lot of that of the standard type stuff. There's more investigation stuff in there now because a lot of students have got all sorts of different stuff they're doing. But yeah, it kind of just sounds like you didn't do a whole lot if all you did was one practice sack before the real thing. So as far as next steps, I'd recommend at a bare minimum do whatever they give you, obviously, and
Yeah.
then chapter review stuff that's relevant to the particular topics being covered. That will be a minimum. If you're crushing through that and then can continue on with other stuff, you've got my practice sacks that are in there. Hit the investigation section or the practice sack section, depending on if you know which one's going to be which. Maybe a healthy balance of both, because it sounds like you weren't really told which one would come up.
Yeah.
Yeah, I think that'll probably do for now as far as advice until I say the actual thing.
I don't
Once
think that they give it back to us. Like they give it, but like you can't take photos.
what a scam. Do it
Yeah.
anyway. Just sneak the phone in. Google Glass, Google Lens, do something to get it
Yeah,
in there, or at the very least, like write down how much time do you have with it.
I don't know. He hasn't even given it back, so
Yeah, just photographic memory, just blink a lot and then imprint it into your brain and see what you can. Yeah, do whatever you can to get it. I hate when schools do that. It's ridiculous. It's like
yeah.
they think their tests are really really cool, and it's like, oh, no one can copy me, and then they realize that ATAR rocks are then doing it anyway.
Yeah.
Yeah, all right. I guess that'll have to do for now then. Keep me in the loop with how that's going. I will say just doing chapter reviews off rip is a really good way to figure out if you're actually getting the content or if it's just that the chapter sections are pretty easy. Because chapter sections are like one or two new things, and you kind of know every question is one or two things. Chapter review is where you're basically now essentially doing a mini sack there. So that'll be a nice little indicator for you for next time. Okay.
Yeah. And like I feel like whenever I'm doing like questions from the exercise, it's fine. But then when it comes to like the actual site, it's just like everything like leaves my brain.
Yeah, I hear that a lot. And so that's the recommendation I give to a decent, like when I don't know exactly what's going wrong, that's the thing that's usually the issue, which is you're doing the chapter sections and there's only one or two things in there. So it's pretty easy to know you've got like two choices at most on how to solve the question. Whereas with the chapter review, it's a lot more broad. And I find that a decent number of people realize they fall short in the chapter reviews. And then the question now becomes, okay, now we got to essentially stop thinking about things in terms of, oh, it's chapter 16E, so I should do these things, versus, oh, I have this key information, and so I should do these things. And that's
Yeah.
what I've written the guides to be for. They're very much in a way where, oh, it's when you have to determine initial something. I follow this. It has nothing to do, like I never mention chapter stuff unless it's at the very beginning to show you where to practice it. And it's for that reason. I want to sort of disassociate the chapter with the actual concept. So maybe have a go and see if you can use those more so. Like we'll do one run through of the chapter review stuff yourself. Do another with that guide as a little resource and see if that helps.
Okay. Yeah.
Cool. All right. Otherwise, I'll leave you to it. Yeah.
I also got one more question.
Oh yeah. Yeah.
When are we gonna start like exam stuff together? Like as the group? Like when are we gonna start that? Because it's soon.
Yeah. Class two.
Okay.
Class two. Every one of those from here on is going to be exam stuff. It'll be tech active one week, tech free the next week. I said that in the wrong order, but you know, it'll round robin between tech active, tech free. Yeah, that's the plan for that one.
Thank you. Yeah.
No worries. All right. Hello, hello. How's it going?
And,
Having fun?
yeah, well, I'm only on the first question, but
Okay, so you are doing this stuff. Yeah, cool.
yeah.
Was there anything in particular you wanted me to have a look at?
Uh, Let me have a look at the thing real quick.
Hmm.
So this is from like this is basically the whole of chapter 16, right?
From E onwards. So the previous before E, so 16A to D, we did in the previous class.
All right.
Um, but
So
you don't really need anything of those to do 16E, I don't think.
so C to E you're saying, right?
No, so A to D is stuff previous.
Okay.
E to chapter review is what we've just learnt.
All right, let me just have a look at 16 here real quick. I'm
Oh, okay,
actually
yeah.
learning most of this in year 10 science right now, so
Yeah, you would because I found it really interesting that in physics specifically they start putting derivatives in there.
yeah, because yeah, we've like they've been telling us about like area under the graph because I'm doing like the selective as well, and everyone's just kind of astonished and like, oh, this is kind of cool.
No,
And then
that's
yeah,
good. You love it when you see a thing already and it's like, yes, I've got that foundation now. I can I can learn
yeah,
it much faster than everyone
yeah.
else.
Actually, like in one of the so there was some other like formula that Shed taught us like like trapeziums and stuff.
Yeah, yeah.
But yeah, so obviously you can estimate the area under a graph, and then I actually use like real integration. And
Nice.
The funny thing was I didn't get the marks because like for some reason the scheme says you have to estimate it, but then
Yeah, if it
he said like, oh, well done on like knowledge and stuff. And I'm like, okay, sure.
Yeah, the wording of the question there will inform that. Now, I mean, obviously, the other part of it was you weren't taught it in that class, so it wasn't assumed to
Yeah,
be
I mean,
required.
actually the thing is,
Yeah,
we didn't expect us to know integration, so
yeah, correct.
yeah,
So that was you just being a bit cheeky, but yeah, um, cool. Because you would have that mark anyway. You knew what the required things were for that.
yeah,
That's nothing. That's just a bit of fun. But okay, so this sort of stuff will be pretty chill for you then.
yeah.
Was there any concepts that were coming up there that were a bit weird as far as like the interpretation of how to describe what's happening?
Yeah. I mean, I guess
Yeah.
because like you know how you were talking like about the origin and stuff, right? In that one question where like
Hmm.
we were doing like the velocity and then like the direction and stuff.
Yeah.
I was like not sure like if you'd always use origin or would you like use it in the context of the question?
Yeah, so you'd well, that's a good question. I'm pretty sure every single question will call the starting point the origin. So you should never need to use a different word for your starting point. But if for whatever reason they call it something different, like the start of a racetrack or whatever, maybe you'll be better off saying the start of the racetrack. Is that what your question was? Like,
Yeah, like you
yeah,
okay, so if you look at exercises like 16E, right?
yeah,
You know how there's so let's say question two, right? There's like the distance it's like the position of the train from
hmm,
the ticket office at a station.
yeah,
And so when it goes back down towards like after x is equal to 5, it starts going down. I mean after t is equal to 5.
yep, yep.
And would you want to say it's towards the door of the ticket office or like towards the origin?
Um, I would have written towards the origin. Saying door of the ticket office is definitely more specific and won't get you any. It won't. It won't ever be a bad thing. It can only ever be a better thing than saying origin, because you're being more specific. Um, I will say I would have still said Origin anyway, and then if I had time, go back, like put a star on it, and then go back when you have time, and then you can like really refine that. That'll only matter as far as pretty much only as far as study score goes, because when you're getting a percentage, like you answering it slightly better than someone else doesn't mean you get a more favorable scaling. It just means that you get the same percentage.
Yeah.
Um, but yeah, no, it's a good question.
And
Um,
then like okay, so again like on question two, right?
yep,
So 2AI, which is like the like train's velocity between the
yep,
interval of t is equal to 0 and t is equal to 2.
yep.
Like even though we can see it was 30 it traveled at 30 kilometers per hour, would we have to convert into meters per second or
Um,
because
it
like science at least like that's what we do, like it's always meters per second for velocity.
Yeah, you would have freedom to go with whatever. If it doesn't specify a unit, then give the whatever unit makes sense. Like it says kilometers and hours here. The natural thing to do would be to kilometers per hour. Um, Converting that to meters per second, I would say again, that's probably another thing you might star and then come back when you have time for it. Um, yeah, I wouldn't.
Yeah.
I would just leave it as kilometers per hour. It's a fairly standard unit.
Right.
Yeah, because like I get what you're saying, which is you want to bring it back to SI units, but um, yeah, I I think you'll get it either way. I don't think there's going to be a preference.
Okay, cool.
Yeah, just keep that as kilometers per hour because it's less chance of failure. So what's that? 3.6 is a division, I think. Kilometers
Yeah,
per yeah
it's divided by 3.6 when you're converting to down in meters per second, and it's multiply
yeah.
3.6 if you're going up to
It's been a
kilometers
while
per
since I've done the done the physics on these. No, it's cool.
hour.
No, physics is good fun. Are you going to go into actual physics because you called yours science? Yeah.
Yeah, next year I'm doing so course confirmations just happened, so next year I'm doing methods,
Mhm.
specialist maths,
Yeah,
which is gonna be a little bit scary.
you'll be
Phys
fine.
physics, English language, and I was already doing accounting 1, 2 this year, and
Yep,
I'll be doing PE 3, 4 as well. So
nice.
yeah, it's gonna be two decently easy subjects and
Yeah.
four pretty sweaty subjects. So we'll see how
Well,
it
I
fares.
mean, you're doing good with methods. With me, it was methods and physics were my highest at 39.
Yeah,
And then yeah, like accounting, I did accounting as well. It
yeah.
was, I think it was like a 33, 35 maybe. I don't really remember.
Accounting is
Um,
like one of the subjects I feel like if you have like a really good understanding of it, like if you have like 100% understanding of the topic, you're gonna do really well.
yeah.
But then sometimes like if there's even like a little gap in like I know if I even forget to like revise one thing before my test, that could be the difference between like a 90 and like 75.
Oh god, yeah. I mean, part of that's obviously, of course, going to be the fact that the marks available aren't particularly high, if I remember correctly. Um, like your percentage points are going to drop a lot based on the fact that it's out of 20, for instance.
Yeah.
Um, but yeah, no, I don't remember
And
too much about how why accounting dropped, but you'll
the thing
obviously.
is like obviously like at normal schools, I reckon a study score above like 30 is respectable.
Yeah.
But then at these selective schools, I don't know what the like thing is, what the go is with the environment. Like if you don't get above 40 plus, they just think you're like stupid. And I'm like, damn. But
Well, I mean,
I
yeah,
actually hold up pretty well. I score like usually the best of my classes, or around the best of my classes, but still like
yeah. I mean, if you're doing that, then you're definitely keeping up the standard for sure. Because 40 is it's probably still top 9% of the state. Um, and it's of the state specifically. So if I remember correctly, by the time you're in Unit 3 and 4, there's about 20,000 students in a little over 20,000 students doing the Methods 3-4 exam.
yeah,
So you're looking at, yeah, effectively 10% of that. So what's that, top 2,000?
top 200, yeah. Oh no, 2000, yeah, my bad.
Yeah. And so, you know,
Yeah,
definitely
and
high up there.
like there's a like last year at Ducks, right? He had 450s.
Nice.
His lowest study score was 45, and I was like, oh damn.
Yeah. Yeah. That's,
Nah.
it's a lot. Like, yeah, if you ask him how much he put into it, I mean, it's
Yeah,
good to have these goals, but you've also got to realize what it takes to get them.
I never used to see him outside actually. I never saw him outside for the whole year.
Yeah. Yeah, have a chat with him, see how he achieved it, and then make a personal decision based on just how much it's worth it for you. Because, yeah, awesome, shoot for 50, shoot for whatever you want to shoot for. There is definitely diminishing returns. Like hitting a 49 is easy, much easier than hitting a 50, for instance, just because
Yeah,
you're at that upper end of the bell curve. You're the third standard deviation as opposed to the fourth standard deviation.
yeah.
Um, and so, yeah, definitely a
And
lot.
yeah, just a question about that. So Unit 2A triple I, right?
Yep,
So he's going from 80 kilometers to like negative 40 kilometers from the relative to the ticket office.
yep.
So would you measure his like velocity as like minus 120 on 3?
Minus 120. Yeah, yeah, it's definitely negative. That's for sure. Because the displacement is overall net negative.
But the okay, so but the displacement is just like so displacement from the start of the interval, right?
Uh, well, yeah, because you're doing go from 5 to 8, and so you're
Yeah.
going from 80 and dropping down to negative 40.
So that's
Because you're going from high to low, that's a negative velocity. Because velocity is always slope.
cool. Yeah, so that should be negative 40 kilometers per hour. Yeah.
Yeah, and so essentially, when you're describing that journey, even though it's going down, you would say that it's moving left towards the yeah, you could even say specifically left towards the front door of the ticket office because you know it's already not at the ticket office. You know it's already 80 kilometers um, in the right direction. So
Okay.
Yeah, they're
And
kind of
okay, so for 2B, right? Can we just go through that together? Like, I'm just gonna tell you what I got for 2B.
shoot it. Yeah, go.
Yeah, so I got so I'm not gonna say ticket off, I use Origin.
Yep.
So I said the train traveled at a velocity of 30 kilometers per hour
Hmm.
away from the origin for 2 hours.
Yeah.
And then I said it traveled away from the origin at a velocity of 20 over 3 kilometers per hour for 3 hours.
Yeah.
And then I said it traveled towards the origin, back towards the origin uh, at negative 40 kilometers per hour for 2 hours. And then again away from the
Oh,
origin.
yeah. Okay, so you split it up into two separate. Yeah.
Yeah. Can you split up or should we just like join that last bit together?
You can do either. I was expecting you to do from 5 to 8, and the wording you would do for that, and I'm saying you could do either, but the wording you would do for that would be to say that it starts moving in the direction of the origin, or left to, yeah, in the direction of the origin. That way, you're not shooting yourself in the foot when it goes past the origin. It's going in that direction as of t equals 5 hours.
Okay, yeah.
Um, but yeah, this is more like very semantics around it. So you got one fine. What your
Yeah.
answer was fine. Um, there's a lot of criteria around it. It's not super strict. Sorry, there's a lot of things you could talk about. It's not super strict.
Yeah. I feel like it would help if they had given like a direction, like a north or south.
Yeah, I mean, if they do, that actually makes it harder for you because conventionally positive is right and negative is left. So if they start chucking north and south in there, that's that's tough.
Yeah, okay, my bad.
Unless they say positive is north, yeah. There might
Wait,
be a
so
north-south thing.
velocity is like a vector quantity, just to clarify, right?
Correct. Yeah.
All right, cool. Yeah, because
So
that's why you need some sort of direction on it when we mention.
yeah, yeah, that's correct. That's why we're saying with respect to origin, which is I like that you're saying relative to origin because you're starting to physics terms. It's have you started doing like relativity frames of reference in physics in science?
The elective only started in this semester, so I've only been
Yeah.
doing
Okay.
4 weeks. So
Yeah,
I'm
because
not I'm not a veteran or anything, but yeah.
yeah, because using the keyword relative is very common in that particular area of study. Because the idea is that you can only ever measure speed with respect to a certain frame of reference, which is like you're stationary on the Earth, sure, but the Earth's spinning, and the Earth's also moving in space. So really, the only way you can measure speed is relative to whatever you consider stationary. But
Okay, yeah.
that's a thing for later. Cool. All right, that's about it then. I'll um I'll hop back in the main room. If anything comes up, I guess you can join me there. Otherwise, we got about 7 minutes until end of class.
Yeah, all right, cool. Thank you.
Wait.